reason if you wanted to do that. You could do that. You can express any of them as a function of time. More specific example is going to be useful. I could express, for example, U as a function of temperature and volume, or U as a function of temperature and pressure. And any such relationship means that there's a relation between the differentials of those three quantities. That means, for example, this expression means that I can write the differential of U equals the partial of U with respect to one of the two variables, keeping the other constant, differential of that variable, plus the differential, the partial of U with respect to the other, keeping, in this case, temperature constant, dV. This expression here means that I can write du as partial U with respect to T at constant pressure dt plus partial U with respect to P at constant temperature dP. And any such differential relationship can be translated to any kind of derivative I want. If I want to take derivative of this with respect to A, I could have partial with respect to TA. I would change this. Partial U with respect to A, partial T with respect to A, partial V with respect to A. This is relationships for behaviors at a point, because a point is a closed system. If I'm talking about an open system, then I need also a variable for the extensive properties. That's usually either the number of moles n or the mass. If I use per mole, probably would have been n. So we write here for open systems, to specify state, we need to add an extensive variable. Now you could be strange and add the total internal energy or something like that, but usually that is n or n. And in this case, the partials is always keeping constant everything for which I'm not taking the derivative. So if I take the first relation, it would be U equals U of T, V, N. So in this case, the differential of U would be partial of U with respect to T, keeping constant not only V molar, but also N dt plus partial of U with respect to V molar. Oh, oops, sorry. One mistake. No mistake, but really we shouldn't be talking per mole if I have an extension. So do it like that and I'll translate in a minute. So let me do it this way. This is not the per mole, this is the internal energy of the system, the temperature of the system, and so on, volume of the system. So du, this is the, if you have an open system, you write the equations for the total amount of the thermodynamic rate. So this will be partial U with respect to temperature at constant V N dt plus partial U with respect to total volume at constant T N dV plus the partial of U with respect to n at constant t v dn. And some simplifications here. We can write things in terms of molar quantities now. The actual quantity is what? U is molar times n. What is n here? Constant. So I can replace this. Okay, slow down. Let me give you a chance to catch it. So finish writing this and we'll continue. If I go too fast, just raise a hand, guys. Sometimes I catch myself. I've never been accused of going too slowly. It's okay. Okay, so we can write total internal energy per mole times total moles. Notice that the partial is with constant n. Since n is constant, I can pull it out of the derivative, so you can rewrite this as n partial molar u with respect to t at constant v and n. Furthermore, since n is being held constant here, keeping constant v and constant n means also your ratio v over n is constant. So I can replace this to what would be the molar derivative, the same derivative I have here, okay, comma n. What about this guy? U is n u underscore. V is n v underscore. So this one, you can write partial n u with respect to nv molar, all that at t n constant. But since n is constant, I can pull it out of the derivative here and out of the derivative here. Careful, you can never cancel inside derivatives. Don't make the mistake of canceling inside the derivative. You have to pull it out, if you can, before you can cancel. If you can't pull out, you can't cancel. So, das ist anders schon, so, factor it out, and then you can cancel. So this becomes partial u with respect to v at constant t n. So it's the same partial I had here, except you have an addition constant n, which doesn't affect molar quantity. So really the n now could have been dropped, both here and here, because these are only intensive variables, so you could have dropped the n for this. So these real partials are the same as what I had in this case. All right? And we actually saw what that was. Do you remember what that is? Yeah, we'll leave it like that for this one, okay. But all right. Another 5 minutes. Let's continue a little bit. So first of all, I'll do some very simple general math, and then I'll restrict for the case where we have 3 variables where they are all connected, specifying any 2 specifies the third. The case for state variables. So for any variable, we have the following properties everybody, of course, knows. Just reminding you. So, math for any variables. For the partial of one variable, and I'll use it now x, y, z as any variables, okay? So the partial of a variable with respect to another, and here I'll put just z constant, but if I had more constants, it would go the same way, is simply 1 over the partial of what I have in the denominator here over the numerator, keeping the same things constant. Okay? Slogan question. Right. The other one is the order of differentiation doesn't matter. So you have partial with respect to z, keeping, let's say, y constant, and I have inside the partial of x with respect to y, keeping z constant. I can change the order of differentiation, and this is equal to doing first, here I do first the partial of x with respect to y. Here I will do first the partial x with respect to z, keeping y constant, and then I will do the derivative with respect to y, keeping z constant. This means derivative with respect to z keeping y constant. This means, of course, with respect to y keeping z constant. So this is your text notation when you have one differentiation after. Okay. Now a couple of obvious things. The partial of x with respect to y, keeping x constant equals 0. If you have among the constant what you're taking the derivative with, it's obviously 0. How about the partial of x with respect to y? With respect to x, keeping y or z constant doesn't matter. Where's that? 1. Exactly. So this is some general methods applicable to everything. I have more variables. Simply the partials would have more quantities or constant, but the same relationships. Three minutes for the triple product. Does that work? Oh, yeah. 3 for triple. Okay. And we'll stop there. Now this is relationships. Right. X, Y, Z are related, specifying any two specifies the rest, which means they have a function of the 3 equals 0. Yeah, all right. Some function. Okay. So if I have only those 3 variables and specifying one specifies all the others, for example, I can write that x is going to be some function of y and z. So I can write dx, what I did before, is partial of x with respect to y, constant z, dy, plus partial of x with respect to z, constant y, dz. And I can convert any of the d's, all the d's, to derivatives as long as I treat all these the same way. So they have to become derivatives with respect to the same thing, holding the same thing constant. So that means, from this expression, that I have the partial of x with respect to y, keeping x constant. So what I'm doing, the differential becomes with respect to y, keeping x constant. It's going to be equal to partial of x with respect to y, given z, and this dy becomes partial y with respect to y, keeping what constant? X, plus partial of x with respect to z, keeping y, and then partial of z with respect to what? The same thing here, with respect to y, keeping what constant? X. Well, there's a reason I did the quick math in front. What is this equal to? 0. Dx with x. So this is 0. How about this guy? So, follows that dx with respect to y at constant z equals minus moving them to the other side, or so dx of partial x with respect to y at constant z equals moving this to the other side minus 1 times that product, but I will rewrite the, well, okay, I'll do it. Okay, so minus partial x with respect to z at constant y times partial z with respect to y at constant x. I will rewrite the right-hand side as 1 over, this I write as 1 over partial z with respect to x, and this 1 over partial y with respect to z. So this is equal to minus 1 over partial z with respect to x at constant y, and this is 1 over partial y with respect to z at constant x. And then I'll move this to the other side, and we have a very nice cyclical relationship which is easy to remember. So from here follows that I leave that as it is, partial x with respect to y at z. I'll write this term next, so that's partial y with respect to z at constant x, and then I'm writing this guy, partial z with respect to x at constant y. All that is equal to what? What is left on this side, which is minus 1. This is the so-called triple product rule. Notice, okay, at some point I'll release videos and you'll see the thing of me breaking chalk. All right. So notice the cyclicality. X, y, z constant, then y, z, x constant, then z, x, y constant, equals minus 1. It looks a little bit similar to the chain rule. It's not the chain rule, and I want to make sure that you don't confuse the two, so we'll do that next time. Oh, yeah, and actually, we need to talk, forget about this. If you're, let's say, Taylor, let's figure out if you're going to have Taylor, no take care of.
Yeah. I said yeah.
So, well, let's.